Okay, so in this video, we're going to do a couple of vector applications. So here are two different things that I want to make sure that you kind of just know. So if you're given this vector v, which is equal to x comma y, you can find the magnitude by taking the square root of the components and the sum of the squares of the components. The direction, you can find it by taking theta equals tan inverse y over x. And this is basically what we've used for polar coordinates. So it kind of makes sense for us to use it here. You do have to be careful with the value of theta, because remember that tangent inverse are only going to give you angles in quadrant 1 and in quadrant 2. However, vectors are not only going to point in that direction. You can also have vectors pointing in this direction, vectors pointing in this direction. It really depends. So for the most part, sometimes you might have to add 180 to the angle. It really just depends on where exactly the vector is. So you have to use a little bit of geometry. Now, one of the things that I want to be able to do is I want to talk about forces. And if you remember, a force is actually a vector. Okay, so we're gonna briefly talk about them, and then when you talk about and when you get into your physics courses, you're gonna be able to talk about them a little bit more. So before we start talking about it, I want to talk about two different things that you may have forgotten from geometry, which we're gonna use in this particular example. So let's say you have these two lines. These lines are parallel. Okay, so they're going in the same direction. They're never going to intersect. And then you have a line that just kind of crossing both of them, and this is what we call a transversal. Okay, so usually by some geometry, okay, from either used in high school or in trig, you can see that two interior angles that are alternate, which is what we call alternate interior angles, are the same if you are under these conditions. So if you have two parallel lines and you have a transversal, let's say call this angle A and an angle B, here angle A is equal to angle B because they're called something called alternate interior angles. Okay, so this is kind of what we learned in geometry. So what I'm gonna do, and the reason why I'm doing this is because it's gonna be very helpful in the next situation that I'm gonna give you. So first, I'm gonna give you the scenario. I don't want to give you just formulas. I want to show you where the formulas are coming from. You may understand it or you may not, but that's fine. I just kind of want to give you a little bit of a gist of where these things are coming from. So the type of problem that we're really going to be working with is you have an incline, okay, at a particular angle, maybe theta, and then you're going to have like maybe this box, and this box is just going to be resting on the incline. All right, so you have this box right here. All right, so I'm going to draw like a triangle. Notice that this is going to form a 90-degree angle. Okay, all right, now for the sake of the simplicity of this problem, let's call this beta. This is another angle beta. So you have angle beta, theta, and 90 degrees. We know that this all should add up to 180 degrees. Now, here is where the physics comes in. So the first thing is that this box is exerting a couple of forces. So the first force is gravity, which basically points all the way down. So this is what we call the force due to gravity. Okay, so I'm gonna write force due to gravity. So that's basically kind of like the weight of the box. Then you also have two different components for this type of for the gravitational force. So you have one. So with respect to this particular box, you have something called the normal force, which is basically perpendicular, okay, to this particular box. So is normal force. You can see that this is perpendicular, and you also have another force, and the force is what we call the parallel force. So this parallel force can be maybe a force that's due to friction, or force you maybe are pushing this box. Eventually you'll push it. So I'm gonna write P for parallel, N for normal. Okay, so this is basically what we have. Let me make this a little nicer. I want to make sure that I write a really nice triangle. So this arrow is pointing all the way down. Okay. All right, kind of good enough. All right, so now what we're gonna do is that there's a couple things that you can kind of see from here. So the whole goal is to try to figure out what the normal force would be and what the parallel force will be. Because if you can see, if I know what this vector component is, and I know what this vector component is, the sum of those two components will give me the vector for gravity, okay? So this is how we're gonna do it. If you can see this blue line, if I were to extend it, you see this blue line, and you also see this black line. These lines are parallel lines, okay? So these guys right here are parallel lines. They're going in the same direction. You can also see that this hypotenuse, I can kind of extend it a little bit. And you can see that that's kind of like a transversal. So if you think about this, you can kind of see that this angle right here is going to be equal to what angle? Well, this angle right here. This angle right there is beta. You can see that you have a right triangle. I don't know if you can see that. You have a right triangle. This angle was just beta. If this is beta and this is a right triangle, so you can see that this triangle right here, this big triangle, has angles of beta, 90 degrees, and theta. So then if this is beta and this is 90 degrees, then that means that this angle right here should be theta. So that angle right there is theta. So that means that this angle is the same as this angle. Now, it doesn't look like it because of the way that I drew my picture. But they're actually the angles by alternate interior angle. So this guy is beta and this guy is beta. And then you have this guy to be theta. Okay. So now what you can form is another different type of triangle. So you can cut. What I can do is that I can bring this vector for parallel and kind of switch it around over here. So let me go ahead and bring this guy over here. This vector is also a parallel vector. I'm just bringing it up. I'm bringing it all the way to the bottom. You can see that I form a right triangle. And now you can see that this angle itself is angle theta. And I can easily figure out what my force due to the normal force is going to be, and I'm also going to know what my parallel force is going to be just by simply figuring this guy out. So this theta, so I can find first maybe the sine of theta. So I'm going to take the sine of theta. Okay, so this is going to be equal to the opposite, okay, which is going to be the normal force. Oh no, that's wrong. The parallel force, because the opposite is the parallel, divided by gravity. So this is going to be the force due to gravity, Fg. Okay, and now you're going to move that over. So I have the parallel force is going to be equal to Fg times sine of theta. Okay, so I'm going to leave that for now. And then I'm going to find the cosine of theta. So the cosine of theta is going to be equal to the adjacent, which is now the normal force, divided by gravity. So I move that over. So the normal force is going to be equal to Fg times the cosine of theta. Okay. Now, if you think about this, this guy is just basically the weight of the box. So weight is a force. Oops. Weight is going to be a force. So if I know the weight of the box, then I know what this hypotenuse is going to be. So the weight of the box is basically going to be the magnitude of whatever that box is. So that I can rewrite this now as the normal force is going to be the magnitude of whatever the vector is times the cosine of theta. Oops, there shouldn't be an equal there. So times the cosine of theta. And then the parallel force is going to be the vector component, so the magnitude times sine of theta. So now we have formulas for both the normal force and the parallel force, okay? Or the components, okay? So now, if I were to add these two together, then I would get the force due to gravity, okay? So if you got that, that's great. If you didn't get this, this is what you need to know, okay? These are the formulas. Okay, so now let me go ahead and do an example where you can actually figure out all these different things. I have a 60-pound box that's resting on a ramp that is inclined 16 degrees. So rounding to the nearest tenth, find the following. So we want to find the magnitude of the normal component of the force, and we want to find the magnitude of the parallel force to the ramp. Okay, So basically we have the same scenario. You have this box that's resting on an incline at 16 degrees. So you have this box, and then you have the force due to gravity. We know what that guy is. The magnitude is going to be 60 pounds. So that's the weight, okay? So you want to find the normal force, okay, that's basically perpendicular, and you also want to find the parallel force. The parallel force is parallel to the ramp. Now, luckily, we have those values already. So we found out these formulas, so we don't have to rederive them again, okay? So the normal force, okay, which is going to be the magnitude, it's going to be the magnitude of the box times the cosine of theta. So this is going to be 60 times the cosine of 16 degrees, okay, and we want to round it to the nearest tenth. So we're going to take 60, multiply it by the cosine of 16 degrees. That's going to give me 57.7. And since this is a unit of force, force in this case will be pounds, so this guy would be pounds. And nearest tenth is just 1 decimal. And now we want to find the magnitude of the parallel force to the ramp. So that guy, the parallel one, is just going to be the vector sine theta. Okay, so this is going to be 60, the sine of 16 degrees. So 60 sine of 16 degrees. So that's going to be 16.5, and this is going to be pounds. So the answer to this problem actually is very, very basic. You're not really doing a lot of things. Obviously, if you're moving the box or you're doing a lot of different other things, then the problem will get a lot more complicated. But I kind of wanted to show you where these formulas come from. So kind of deriving all of these different types of formulas and being able to apply them to a new problem.